Okay, so good morning or good afternoon. It depends on where you sit right now. My name is Miloslav Čapek. I'm from Czech Technical University in Prague. And today I would like to tell you something about theory of characteristic modes. So actually this talk is an extended version of invited talk I had this year at UCAP. And well, within this talk, you will see how to utilize the famous equation, which is depicted here, xi is equal to lambda ri, which is the decomposition into characteristic modes. And together with that, I would like to focus on to clarify what characteristic modes truly are, what are their strengths and weaknesses, and finally, I would like to focus on the future development of this theory. So here, by the way, on the on the right-hand side, you can see a characteristic mode, in fact, the dominant one, for a fractal shape of fourth iteration. So you can see that with this theory, there is also some beauty coming in, and you can appreciate very nice patterns of electric current density on your shapes. So as for the outline, I have decided to closely follow the chronological order. So I will start with early works to recapitulate what were the proposals, how to decompose characteristic modes, how to get them for different operators, and then I will quickly move to modern era, where we will show what are the current trends, what is implemented basically in contemporary electromagnetic simulators, and then we will focus on recent findings and future challenges. And after that, I will conclude this talk with some topics related to community and plans we have for the near future. Please notice that all results you will see in this talk, mainly all the graphical results, all the curves and everything, all was generated with two atom. We are developing here at Czech Technical University. And if you like, you can download the free version from this webpage, antennatoolbox.com. And you can freely evaluate all the examples you will see here today. Finally, on the right, what you can see is rectangular plate, and this example I will use quite often today to demonstrate the different parts of the theory. And directly for this shape, you can see here how different characteristic current densities look like. And below, you can also see what is the absolute value of the eigenvalue and also the type of the characteristic mode, either capacitive or inductive one. And this is something I will explain in detail during this talk. So before that, let's start with the beginning of the theory. And in fact, one of the first mention you can find is from 1948 in a book written by Montgomery, Dick, and Purcell called Principles of Microwave Circuits. And in that book, on page 328, you can find in equation 94. If you look closely at it, what you realize is that it's a proposal of how to decompose a scattering operator into modes being orthonormal in far fields. And actually, this is exactly what we typically need and what we want from a set we call characteristic modes. So for scattering operator, it was in 1948. And then later on, and notice that it was 20 years later on, Garbacz came with his PhD thesis, and in that he proposed equivalently to decompose operator he called perturbation operator. Nowadays, we would call it transition matrix. So that was in 1968, so 20 years later. And actually, in that PhD thesis, you can learn basically the complete theory of characteristic mode. All the properties are mentioned there, and the complete analytical theory is devised. Of course, at that time, Garbacz has no approach to effective numerical procedure to evaluate arbitrarily shaped objects. And this is what came with Harrington and Maut's paper from 1971. So 1971, we sit here. And then you can find in that paper it's mentioned in the footnote as paper number 3, that we can, once again, equivalently to decomposition of scattering or transition matrix, decompose impedance matrix instead. And with impedance matrix and with method of moment implemented and incorporated, we have a free approach to decomposition of arbitrarily shaped antennas. And this was the true beginning of modern era of characteristic modes, because with this theory and with this proposal, we can basically calculate characteristic modes of whatever we like. So, well, now let us compare these 3 approaches, because they are equivalent for certain cases, but also detailed comparison of them can reveal some important differences. So first, once again, let's follow the chronological order. So the first one on the very left is decomposition of scattering operator S, or you can freely think of decomposition of scattering matrix instead. And you can see that scattering operator is something which is representing incoming spherical waves to outcoming spherical waves. And this is really what is the map of scattering operator. And then its decomposition into characteristic modes from Montgomery's book is really this one, with S being eigenvalues and FONs being characteristic vectors. Here, the characteristic vectors really describe directly the far fields. And the situation is pretty similar for transition operator T, where the only change is that T is a map from regular waves, here denoted by bold A, to once again a set of outcoming spherical waves. So that's the map done by a transition operator, but the decomposition formally is the same one. So once again, you will get a basis of or set of vectors. We call them characteristic vectors, and they describe here directly characteristic radiation patterns. Finally, on the very right, something which is known a lot and used a lot today is the decomposition of impedance operator, where the map is normally from surface current density to incident electric field, or equivalently to a scattered electric field. And then the decomposition is a different one. There is the Z matrix on left, and there is a R matrix on the right. And I will spend some time with this equation during one of the following slides. But what I wanted to point out here is a very important observation, that the 2 problems on the left and in the middle, those are scattering problems. And with decomposition or with representation in spherical waves, we have to keep in mind that this is strictly valid only outside of the smallest circumscribing sphere, which is highlighted here by the gray color for the circle of the radius r. So only quantities which are outside of this circumscribing sphere can be completely represented in this in these bases. But we don't have this assumption for the decomposition of the Z matrix. And therefore, we may think that this antenna problem, in fact, has no assumption like this, that the quantities being inside the circumscribing sphere are maybe ill-converging. But during this talk, you will see that this is the case as well. And we have to be very careful with investigating quantities which are tightly related to a near field with characteristic modes, such as Q factor of your antenna or input impedance and so on. And the reason is, once again, that all these 3 decompositions should be equivalent, and therefore even the right one should somehow share the assumptions of the left one. So only quantities sitting outside of the circumscribing sphere are well converging with this theory. Okay, so now we have our matrices. Just pick one you like, or pick the one you have approach to. And now well, how to decompose it into characteristic modes. It's an eigenvalue problem, or it's a generalized eigenvalue problem. And if you are able to accomplish it, you get this property, meaning that the T matrix in this case, or the transition operator in this case, is diagonalized. What does it mean? It means that the matrix, which was originally dense with non-zero entries everywhere, is diagonalized so that you get a matrix which has non-zero entries only on a diagonal. All other entries, all the off-diagonal terms are zeroed. And this is extremely nice because together with your eigennumbers sitting on the diagonal of this matrix, you get also eigenvectors. And this could be extremely compact and useful representation of any problem which can be described by this transition matrix. So being more specific, consider a rectangular plate made of perfectly electric conductor, which is depicted here on left. And let's call it omega, but it doesn't matter actually. And also consider only one principal cut for phi being equal to 0. For this structure of electrical size Ka being equal to 1, where the Ka is electrical size of your obstacle. So imagine that you have your rectangular plate, then A is the radius of the smallest circumscribing sphere in which you can entirely place your rectangular plate, and K is a wave number in vacuum. So this is Ka, and for Ka equal to 1, here are the characteristic radiation patterns, dominant one, first, second, third, and so on, really depicted in a plane highlighted here with the phi being equal to 0. So what we have here, first of all, you can really confirm that all the radiation patterns are orthogonal to each other. So this is something we would expect probably from before. Also, normally, together with this, you are normalizing your eigenvectors, your characteristic vector, so that they radiate unitary radiated power. But I have decided not to do it here, so that all the shapes of the characteristic modes have comparable size and they are clearly visible. Instead, I'm showing you what is the amount of radiated power for the corresponding characteristic mode, and you can see that it's very rapidly increasing number, meaning that the first mode is radiating unitary radiated power 1 watt, but the fifth mode is radiating 1/1000 of watts. So it's really a small portion as compared to the dominant mode. And this is indicating that truly this basis could be extremely useful for scattering problems, because this is indicating that you can typically need only a few of modes to express your problem in this basis completely. And this is typically what we need from our basis, to have really a compact representation, meaning that only quite a few modes can be used for that purpose. Okay. Together with the eigen numbers, and their meaning will be also explained later, and together with characteristic radiation patterns, you get also characteristic currents. So those are the source currents sitting in the region of your structure, so here on the rectangular plate of the aspect ratio 2:1. And you can gather a lot of information from visual inspection of these currents as well. For example, the first characteristic mode, represented by this current sitting on the very left, is clearly a capacitive mode. You can recognize that from the fact that actually the surface charge density is very nicely separated to the bottom and to the top edge, and it's really a capacitive mode. And the same is repeated for the second mode, which is only rotated by 90 degrees, and then for the fourth mode as well. But the third and fifth mode, they are clearly inductive. And how you can recognize that? For example, focus on the third mode. And if you do it very closely, you realize that there is a loop with the current which is flowing around the perimeter of the rectangular plate. So really creating a loop like this one. And we know from the theory that the loop has typically an inductive behavior. So once again, this is why we really like characteristic modes a lot. Just from the visual inspection, you can realize what are the building blocks of your scatterer and of its potential electromagnetic behavior. You can easily isolate modes you like or you prefer because you know that their performance is what you need for your application. And also, considering a scattering application, we know from the slide before that this could be extremely compact representation of your problem. Okay, now a few words to characteristic numbers and their meaning. And once again, let me compare all three possible approaches. So either decomposition of a scattering matrix S, and here you can directly see that we use, instead of the analytical operator, we use a matrix, so an algebraic structure. That means that we can really numerically evaluate what characteristic numbers are. And also, let me recall that we are still evaluating a perfectly conducting rectangular plate of aspect ratio L to L over 2. And for this case, the electrical size was significantly increased to Ka being equal to 5. Therefore, the eigennumbers, at least some of them, are closer to their resonance. So here left is decomposition of scattering matrix. Then, as you would probably expect, a decomposition of transition matrix T. And finally, on the very right, you have a decomposition of the impedance matrix Z. So let's start with the S matrix on left. For lossless structures, we know from theory that scattering matrix is unitary. That means that by theory, all the eigennumbers should sit on unitary circle. And you can quickly verify that this is really the case. So all the eigennumbers are sitting on unitary circle. This is a very nice property. We can utilize it, for example, for interpolation in tricking. Also, we know that the inductive modes and their eigennumbers are sitting on the upper half plane, while the capacitive ones are sitting on the left, sitting on the bottom half plane. And this is because the eigennumber is negative for, or the real part of the the imaginary part of the eigennumber is negative for capacitive modes, while it's positive for the inductive ones. Also, we can realize that the accumulation point is sitting at 1. And what is accumulation point? That's point where the majority of the eigennumbers and eigenvectors sits. So in this case, it's close to 1. And on the contrary, most being close to their resonance are sitting close to -1. And in fact, the self-resonance happens for -1. Well, the situation for transition matrix is pretty similar. Everything is only compressed by a factor of 1/2, and it's also shifted by a factor of 1/2 along the real axis. But without that, you can see that basically all the eigennumbers are sitting at the same places, and only the axes were rescaled and shifted appropriately. So the capacitive or inductive nature is distinguished in the same way, and everything basically applies. The only change here is that the accumulation point is sitting at 0, meaning that the majority of characteristic numbers have a 0 value in this case. And this may indicate, or this indicates, that the T matrix is typically a singular matrix with a lot of zeros. Finally, the picture completely changes if we look at the right figure here, and if we consider the composition of the Z matrix. And that we can do with some method of moment code. So we get a Z matrix and we decompose it like here. So then the lambda eigenvalues are real valued. So we cannot plot them in complex plane, but we can plot them only like here, that let's say that the capacitive ones, once again, they have a negative eigenvalue, so they sit on left part of the plane. The the inductive one sits on the right part of the plane, and their magnitude in absolute value in logarithm scale is along the y-axis. And what you can realize here that actually the behavior of these eigenvalues of lambdas is quite unpleasant. First of all, you can see that it's a rapidly increasing number, even in logarithm scale. And on the top of that, the accumulation point, well, this is somehow related to this observation, that the accumulation point is sitting either in plus or minus infinity. So this is causing also a lot of problems with algebraic decomposition, because, for example, consider a situation in Matlab where you are decomposing your impedance matrix. That means that the majority of your eigenvalues should have eigen-number equal to infinity. But this is not possible in finite precision arithmetic. So this is actually introducing a lot of problems with precision, dynamics, stability, and so on. Okay, apart from that, we can easily establish equations which are giving links between different formulations. So, for example, to calculate eigen-number in S decomposition can be pretty easily done with the eigennumbers known for the T matrix decomposition. The similar is true for the link between Z and T. And this is completing the link between Z and S as well. We can also easily go from the T matrix to S matrix with this relation, but it's much more complicated for expressing, for example, T matrix from Z matrix. But it can be done, and I will show you during this talk how to do it. But before that, let me introduce really some method of movement code. This makes it possible for us to really discuss all the properties of the algebraic decompositions where the impedance matrix has been calculated somehow. So very briefly, let us assume that the yet unknown current density J is represented in a basis here denoted by a letter psi with expansion coefficient i's. And for simplicity, consider that we have only electric field integral equation. First of all, this gives us a very straightforward interpretation of characteristic modes, but also it's very easy to implement it in your favorite mathematical environment. So for now, let's take for granted that we have Z. And either you are able to write your own code and get Z from your code, or you use some professional or academic electromagnetic simulator and you export the impedance matrix from it. Notice here only for completeness that if you incorporate some other method of movement paradigm, not electric field integral equation, but for example, combined field integral equation or some surface equivalence, it may easily happen that the definition of the impedance matrix of Z matrix is much more complicated. And then it's not so straightforward to decompose Z matrix into characteristic modes, because then you cannot utilize that the real part of the impedance matrix is directly the radiation of the structure, and that the imaginary part X of your impedance matrix is related to a reactance. Because, for example, for combined field integral equation, it may be pretty complicated to isolate the radiation part of the impedance matrix. It is not directly the real part of it. So here we have EFIE, we have perfectly we have perfectly conducting obstacles, and we can move forward. So in this case, we can closely follow Harrington steps and consider this decomposition as what we need. So Zi is equal to some eigenvalues times Mi, where M is some weighting matrix, as it is called in theory of eigenproblems. And in our case, from the beginning, we would like to have orthogonal far fields. That means that immediately we will substitute R as the weighting operator, which secures that the radiation patterns are orthogonal to each other. And also, on the top of that, if we prescribe that these eigenvalues should be equal to 1 plus j lambda, we can simplify this decomposition. So we arrive to this equation, which is the well-known formula for decomposition into characteristic modes, where X is the reactance part of the impedance matrix and R is associated with radiation. And how to do it in practice? Well, just in your favorite mathematical environment, it could be a Matlab, Python, Julia, well, basically what you like. You have to employ either generalized Schur decomposition or implicitly restarted Arnoldi method. And these two are the classical methods of how to decompose matrices in generalized eigenvalue problem. And they are slightly different in implementation. So typically we get the first one, or we employ the first one in a case then when we would like to get the entire basis, so all the modes. But if you are interested only in a few modes, which is the typical case that you have a matrix of size 1000 times 1000, but you would like to know only 5 modes, then much faster is to employ the second algorithm, the implicitly restarted Arnoldi method. And only as a footnote here, please be careful with what implicit normalization is used for your algebraic formulation. And notice that this may be not consistent even for one of these problems. So for example, in Matlab, if you decide to utilize generalized Schur decomposition, still there could be 2 different possibilities of how are the eigenvectors normalized. So please here consult the documentation and read carefully of what normalization is used. It could be useful for what we will do in the following. So for now, we have the decomposition completed with some algorithm. We employed method of moment code and so on. And now let's focus on what algebraic properties we get. So first of all, the Rayleigh quotient generated by this decomposition is this one. And you can see that it's a ratio between the reactive power and the radiated power. And this is directly what your eigenvalue is telling about each eigenvector. So it's pretty natural to normalize eigenvectors somehow. And the standard normalization is so that the modal radiated power, the power radiated by each mode, is normalized so that it's unitary. And if you do it like that, then the denominator of this quotient is basically 1. And then the eigenvalue is directly telling you what is the reactive power of the mode. So basically, what is the magnetic stored energy minus electric stored energy multiplied by 2 omega. Well, this is telling you what is the electric nature of the mode. Is it capacitive or inductive? So once again, you can see here directly that we can easily judge from the eigen number whether the mode is predominantly capacitive or inductive, because it gives the nature of the mode. I mean the reactive power. Okay, so let's now study a bit all these information together. For an example, we like a lot, actually. It's a dipole, so let's consider a thin strip dipole like this. And the overall length is L, and the width is L over 50. So it's a relatively thin strip dipole. And this structure has been discretized, its impedance matrix has been calculated, and it has been decomposed into characteristic modes, in our case, in Atom in Matlab. And here, first of all, you can see the behavior of all the eigen numbers. I mean the first 6 eigen numbers in this case. So all are starting in -infinity, so they are clearly capacitive, because we know that for thin strip dipole, all the modes should be really capacitive. And then they are starting to go closer to a 0 axis, or the value 0. And then they cross it at a certain specific point, which we call self-resonance of that mode. And then they become slightly inductive. And well, where is the self-resonance? So the x-axis is in Ka in this case, and you can see that the first resonance is quite close to Ka being equal to pi/2. So the first self-resonance is very close to this point. And then actually the next one is close to pi, and then 3pi/2, and so on. And this is in Ka. And if you recalculate to lambda, you realize that actually the first mode has really the lambda/2 self-resonance, as we would expect from theory. And in fact, the first mode is also shown here. I mean, its current density is shown here, and also it's shown of how it's evolved with electrical size Ka. So 6 cases are shown here, 6 snippets, and they are valid for these dashed lines. So the first one is for this Ka, the second is for this Ka, third for this Ka, and so on. So what you can see immediately is that not only eigennumber, but also the eigencurrent is evolving with frequency. It's changing its shape with frequency. So we cannot consider it being constant, by no means. And for completeness, the same is shown also for the second mode here. And you can see that the first mode is basically the one sinus wave like this. And the second mode has 2 sinus waves like this. So these are the classical modes on a string. Okay, so one possibility of how to show eigen, or how to depict eigen values is like this, but really the numerical dynamics is huge. So instead, we are well used to depict the same information in logarithm scale of the eigennumber in absolute value. And then typically the self-resonances are very close to these dips, because there you are really touching 0, so in a logarithm scale. And finally, extremely compact and I would say quite a nice way of how to parameterize eigennumber is to express it in eigenangle, in fact. And it's done like this. So the eigenangle delta n is pi minus arcus tangens of your eigenvalue. So this is in radians, but I'm showing everything here in degrees, so just recalculate radians to degrees. But then what you get is a very compact representation. So the region spanned by the eigenangle is only from 90 to 270, where the capacitive modes are sitting here from 180 to 270, and the inductive modes are from 90 to 180, with self-resonance happening for 180. So eigennumber is 0, and then the eigenangle is 180. So this is the indication of self-resonance. And you can see that's extremely smooth curve for all of the modes here. And this is very well suited for any visual inspection of how the modes evolve and what is their behavior. Okay, so let me conclude here with highlighting that both numbers, and eigencurrents are evolving with frequency, and they cannot be considered to be a constant. Well, here, just for a completeness, as I mentioned, that any eigenvalue decomposition is especially useful in a case when it's offering a compact representation, meaning that only a few modes are needed to express fully the behavior of your structure. And here we can realize that this is the case for characteristic modes, especially for electrically small regions. So here we have two obstacles. The first one on left is a spherical shell. On the right, we have a rectangular plate. Both obstacles are perfectly conducting. And together with that, I'm depicting a number of characteristic modes with a magnitude smaller than either 10 or 1000. And this is depending on the electrical size. So you can see that, for example, for a sphere, it can be easily in hundreds, I mean the number of modes, which are modally significant, for Ka above 6. And for a rectangular plate, it's also pretty rapid increase. And here I did a fit. So you can see that it roughly goes with Ka squared. So for Ka being equal to 10, it could be easily that you will need 30, 50, 60 modes to take into account for your application. So this is something which is good to consider for your application. Okay, this is only a comparison of two spaces in which we can represent the characteristic mode decomposition. So first is through analytics, and second is numerics. So considering electric field integral equation once again, this is the governing expression for the analytics, and here you can see the algebraic form. So the excitation vector, impedance matrix, and current densities. In the first case for analytics, typically the solution is exact, but unfortunately, we cannot find an inverse to this problem. That means that typically we cannot find such a solution. But on contrary, for numerics, we have only an approximative solution, but we can find it easily. We just invert this matrix, or we decompose it into characteristic mode. So this is the advantage of the numerics. And finally, there are different bilinear forms we can adapt, different inner products we can adapt, and this is just to compare these two words, let's say. But still, the analytical representation can be extremely useful for us, especially in a case that we need to validate our code. So imagine that you have already implemented your method of moment. You decompose your problem into characteristic modes. And now you are at the stage where you would like to verify whether the data you get, the numbers you can collect, for example, in Matlab, whether they are correct. And for that, we have to consider some validation. Well, the obvious possibility is to compare against some commercial software. But this will not give you the perfect validation, because results there were also probably, well, for sure, they were calculated algebraically. So better is maybe to focus on some structure for which we know results analytically. And unfortunately, for a characteristic mode decomposition, there is only one structure, one obstacle of finite extent for which we can evaluate everything completely analytically. And this structure is a spherical shell for surface formulations, or a sphere for volumetric problems. And for your convenience, here you can see the analytical expressions for characteristic numbers for both TE and TM spherical waves. And you can see that they are only products of a Newman and Bessel spherical functions. So this is actually offering a very good way of how to validate your code. And of course, together with eigennumbers, you can very easily get also eigenvectors, I mean current densities, calculated analytically for the spherical shell. Here you can see how the eigennumbers behave when you increase the modal order of Tm or Te wave. And once again, you can clearly observe here that the increase of the eigennumber is extremely rapid. Here, well, just let me notice that here, once again, everything is in logarithm scale. And you can also see of how it varies for different Kas. One of you may actually ask why we have some sort of stairs here. So why are here these stairs? So just let me remind you that we have a spherical shell, and that means that some modes are degenerated because the spherical waves are degenerated thanks to the symmetrical, thanks to the symmetry of the spherical geometry. Here you can see the frequency behavior of eigennumbers for a spherical shell of radius A. First the M mode by blue, and then the TE modes by dashed red curves. By the way, once again, why this is also so challenging example for any validation? It's not only because the eigennumbers are spanning the entire range from -infinity to +infinity. This is the same for any other obstacle. But spherical shell has internal resonances. So those are the specific points in Ka where the behavior of the mode is changed immediately from -infinity to +infinity. So the changing from the inductive to capacitive, or from the capacitive to the inductive behavior. Then on the top of that, for spherical shell, we have degeneracies, as I mentioned. So that means that the first curve is 3 times degenerated. In fact, there are 3 different curves on the top of each other. The second mode is 5 times degenerated. Then the next one is 7 times degenerated, and so on and so on. So actually here you are competing with a lot of problems, degeneracies, internal resonances, huge numerical dynamics. And finally, the smooth spherical shell is typically not well conforming with the discretization we use. Because in our case, we typically employ a triangular discretization. So this gives you a nice, or well, more or less nice spherical shell only for extremely high number of unknowns and extremely high number of triangles. So this is pretty challenging example after all for your validation. And just for the completeness, you can see also how the eigenangles delta looks like for spherical shell. So once again, you can see the internal resonances as these abrupt changes, these vertical lines. Okay, so here I would basically jump to another topic, which is a problem of tracking. And this is actually a problem you will always face too, because normally what you get from your decomposition is when you sweep electrical size or when you sweep frequency, is a picture like this one. And you can see that it's extremely scattered. All the lines are basically switching between each other. But what you would like to see is a figure like this here on the right-hand side. And notice that these are the data really calculated for L-shaped plate shown here in Matlab. So this is a real-life problem, let's say. And what you get normally is really this. What you would like to see is this. And how you can do it. So clearly, you have to incorporate some tracking algorithm, which is basically sorting all the eigentraces correctly. And normally, commonly, this is done with a tracking algorithm mostly based on correlation between different eigencurrents, or in some cases, in some softwares, also on correlation between radiation characteristic modes. So not eyes directly, but far fields are calculated from these eyes. And that's what is used for the correlation. And how it works, basically you calculate your currents for each frequency, you have these sets, and you evaluate a correlation between all eyes at one frequency and all currents at the next frequency, and those correlating most are connected together. And this is producing, after all, a figure like here, so the right figure here. Now you may think that this is sufficient and that it works well. Well, here it's the case, but unfortunately, for more complicated problems, or especially for problems having some internal symmetries, some degeneracies, and so on, it's not the case, and you can easily observe a lot of artifacts and problems with the standard tracking. And for this reason, let me spend some time with a problem of crossing avoidance, which is tightly connected to a problem of tracking. And to be able to really move forward, we will need to employ a von Neumann-Wigner theorem. And you can actually learn all the details in this seminal paper of Neumann and Wigner from 1929. But let's simplify it here, and let's explain the important implications for us on an example which is shown here. So, what von Neumann-Wigner theorem says? Simplified enough, it says that eigentraces within one irreducible representation cannot cross each other. This is extremely important observation coming from quantum mechanics. And notice that it's strictly valid for any eigenvalue problem. So not only for characteristic mode, but basically for any eigenvalue problem. So definitely it is worthy to study it here and try to learn of where are the implications for us. So once again, we have an impedance matrix Z. And first of all, let's show what are the irreducible representations. Imagine further that under certain circumstances, we can modify our impedance matrix, the original impedance matrix, so that it's composed only from blocks. And that means that zeros, really zeros, are sitting everywhere else. So all these white places are filled with zeros. And non-zeros are sitting only inside these blocks. If you are able to find such a matrix gamma, which is able to do this compression, then we call Z matrix as reducible matrix, because it can be reduced to this form. And our matrix Z hat is then called irreducible matrix, or irreducible representation of matrix Z, because we cannot reduce it further. And now, since we have independent blocks, well, in principle, first what we can do is to decompose these blocks into characteristic modes completely independently. That means that doing that, we can save a lot of computational time. So this is the first advantage. The second advantage is coming from a reading of this implication of von Neumann-Wigner theorem, that actually only eigentraces within different irreducible representations can cross each other. That means that eigentrace from this block can cross eigentrace from this block. But two eigentraces which are products of decomposition of a soul of one block, they cannot cross each other. And now, let me only add one important information here. We can decompose a matrix like this only in very specific case, in a case that we have some symmetries present over our structure. So, for example, rectangular plate is certainly a structure with some symmetries, because rectangular plate is structure you can mirror along this axis, and also you can rotate it by an angle pi. And in all cases, you get the same structure as before. Well, for example, a square has also symmetries. There are even more symmetries than for a rectangular plate. Triangle, the same, also symmetries. And for these structures, having some point group symmetries, you can really change this Z matrix into this irreducible representation. For all other structures, I mean for some arbitrarily shaped structures like this, without any obvious symmetries, you cannot do it. And basically, your irreducible representation is the original matrix Z. And now let's read the von Neumann theorem once again for the last time. Eigentraces within one irreducible representation cannot cross each other. So that means that if you have arbitrarily shaped structure like this, and if you decompose it into characteristic modes, you know from the beginning that there should be no crossings of eigentraces. So something like this for the eigentraces can happen for a symmetrical structure. But you know from the beginning that for a structure without any symmetries, you can have only behavior like this. So eigentraces should strictly avoid any crossing. So this actually gives you a very nice prescription of how to implement alternative tracking procedure. First of all, just classify the symmetry groups if there are any. If there are, find a irreducible representation of your problem. I mean, separate it into blocks like this. Then decompose these blocks individually. You gain a lot in computational time. It will be much faster, by the way. And then you can perform a simple sorting within these blocks and put everything together. So here you have some sort of confirmation that this approach is vivid and works well. You have a structure which is shown here in the left bottom corner. It's a rectangular plate, once again, aspect ratio 2:1. But it's extremely poorly meshed to have a simple demonstration example. And also on the top of that, you may notice that even though that the shape is perfectly symmetric, then the mesh grid, the discretization, is not symmetrical. And that means that we cannot basically to reduce the matrix of this problem into some irreducible blocks. That means that from the beginning we know that all the eigentraces should basically avoid any crossings. And we have two algorithms. The left one is the classical correlation-based algorithm from Atom. So in this case, it's still extremely powerful algorithm. You can see that it's adaptively refining the spectrum at points which are either interesting or points which can be potentially somehow switched and so on. And here on left, we have our symmetry-based tracking algorithm, where we knew from the beginning that basically there are only crossing avoidances everywhere. And you can see that it works well. It works for all the stages of the problem. So even for extremely poorly sampled problem in frequency, you get a correct tracking, which is not the case for the left example. And basically, this can be clearly used for tracking. And also notice that for a rectangular plate like this one, so of unsymmetrical mesh, all the eigentraces all the eigentraces avoids any crossing. Okay, so for completeness, the second example is the same shape, but now the mesh grid, the discretization, fully supports all the symmetries of the original rectangular plate. And that means that now, actually, the original impedance matrix, let's consider that it's matrix like this one, is really reducible into 4 blocks. So blocks like this, where this is the first irreducible representation, second, third, and fourth, and zeros are sitting everywhere else. And eigentraces coming from these individual blocks, they are called in this case A1, A2, B1, B2 in point group theory. They gives you a different eigentraces, which are in our case denoted by different line styles. So the first irreducible representation is denoted by solid lines, the second one by dashed lines, then dash dotted, and then dotted. And what we know is that lines within one style, so within one irreducible representation, they cannot cross each other. And if you focus at some region like here, you really realize that it's the case. While eigentraces from different irreducible representations, then the crossing is allowed by the von Neumann-Wigner theorem, and you can see that you can find a lot of crossings for these different line styles. And once again, you can see perfect convergence for the tracking, for the symmetry-based tracking, while it's a bit complicated for the standard correlation-based tracking. Unfortunately, everything which has been said now is introducing one dilemma, one problem. And the problem is with the following. Consider for simplicity two dipoles, which have almost the same length, and this is on the right, and then two dipoles which have mathematically the same length L. And then, if you evaluate the eigentraces for the two dominant modes, for the in-phase and out-of-phase modes, you realize that for the left case, there is very nice crossing. And by the way, crossing here is allowed by the von Neumann-Wigner theorem, because these two traces are belonging to different irreducible representations. But here, we know from the beginning that there should be a crossing avoidance, even though pretty sharp. Almost there is a point, there is a common point where these curves are touching each other. But still, by theory, there should be a crossing avoidance, because they are of slightly different length. Well, it could be just one atomic layer, but they are of different lengths. And this is a problem, because if you start to think about this thoroughly, you realize that you cannot actually have both the continuity in eigennumber and at the same time to have a continuity in eigencurrent. This is strictly not possible. And at the end, you have to choose if you prefer a continuity in lambdas or continuity in currents. Maybe to explain this even more, to give you some specific example of this problem, or where you have to make your choice. Two dipoles, they are of the same length in this case, but the discretization is different. So the left dipole is discretized with, if I'm correct, with something like this. So this is the pattern of the Delaunay triangulation, while the right dipole is discretized with this. And so we can conclude that we have a structure which is embodying the symmetries, but because of the underlying discretization, symmetries are not there. And because it's, from the numerical point of view, unsymmetrical structure, we should expect a crossing avoidance. And you can see that really, if you calculate it extremely finely and precisely, there is a continuous smooth crossing avoidance. Well, for this, I used 2000 frequency points in this very narrow frequency band to really confirm that it's there. And now we have continuity in eigennumbers. What about eigencurrents? So here you can see the first and the second mode. Those are corresponding with the eigennumbers shown here for the first and the second mode. But here are the eigencurrents, and they are measured in the middle of each dipole. So in the center, there is the current density in the y direction measured. And for the first mode, you can see it here. And for the second mode, you can see lines here. And always there is the blue line for the current measured for the blue, for the left dipole. And there is also current density in the middle of the right dipole, which is the red one. And what you can see here is that actually the first mode is in-phased mode below the crossing avoidance, meaning that the current is flowing in the same direction. So you have two dipoles, and in-phased mode is a mode where the current density goes like this. While the out-of-phase mode for two dipoles is that the current for the first dipole is, for example, going up, and for the second dipole is going down. And what you can see here is quite shocking, that the in-phased mode is changed to out-of-phased mode above the crossing avoidance. And the contrary is valid for the second mode, which is out-of-phase below and in-phased above. And this is confirmed here in this table. So the first mode is the top row, and the second mode is the bottom row. And you can see that really below the crossing avoidance, it's in-phased. Then it starts to change its shape. Here, at this particular frequency, there is, by the way, current non-zero only at one dipole and being zero for the second one. And then above, it changes its shape to out-of-phase mode. And the contrary is true for the second mode. So now if we summarize this, that means that we have perfect continuity in eigennumbers. We have very nice crossing avoidance. We are able to track it down and to see it. But eigencurrents are not continuous. And now imagine that you cannot sample your problem in frequency so finely as I did it here. So 2000 samples for Ka of 0.2 or 0.1. So you are sampling in a frequency poorly because you have some commercial software and so on. And in that case, it may happen that actually you calculated your problem only for this frequency. So KL 2.978, and at this frequency 2.995. And still you can see that these two KLs are extremely close to each other. But if you solve it here, and if you use correlation tracking algorithm, you can easily make a mistake and think that actually first mode here is second mode here, and these two should be connected. And that the second mode below the crossing avoidance is the first mode above the crossing avoidance, and connect these two, which effectively means that you will see a crossing you will see a crossing like this for your eigenvalues. But we know that this is not the case, that they should look like this. So this is really a problem of tracking, and it's telling us actually a very important conclusion, that tracking is or should be not important for us. It's not important how the modes are connected at different frequencies, because we live in frequency domain. And at the end of the day, we will sum up all the modes together. And this is actually bringing me to the second part of this talk, that we have already our code implemented, verified, we are able to calculate characteristic modes. But at the end, as electrical engineers, we would like to do something with them. And the last step is that we will really connect excitation somewhere. That means that we will perform a superposition of all the modes together. And with superposition, we normally employ a formula like this one. It's a superposition formula, which can be easily derived from what has been shown before. And this is the important part, where actually the first part of the formula is called modal significance, which is depicted here on the right. And simply said, it is showing the relevance of a particular mode at a given frequency. So, for example, the first mode is very relevant, close to the Ka being pi over 2, which makes sense, because in the vicinity of this electrical size or frequency, this mode is self-resonating. So it's the mode which can be easily excited. The second part of the formula is excitation coefficient, and notice once again that the denominator IRI is typically normalized to 1. So it's not important to have it there, but this is just for the completeness. But the part in the denominator is excitation coefficient, and this is telling us of how the mode is willing, let's say, to be excited by a particle excitation represented by a vector V. And finally, this gives you some weighting coefficient alpha. And with this weighting coefficient, you multiply all the eigen vectors. And actually, we can utilize this formula, or we can generalize it so that it can be applied to arbitrary antenna metric, which is expressed as a quadratic form of this form. And then you get formula like this one with two summations, which can be simplified to this multiplication, where alpha is a vector of these weighting coefficients, and A with tilde is a matrix of modal characteristic quantities for the problem. So imagine that you would like to optimize Q factor. In that case, it makes sense to evaluate a matrix of modal of characteristic modal Q factors, and then this is this matrix A tilde, and these unknown coefficients alpha can be found with some quadratic optimization. So this is extremely useful for some feeding synthesis problems. Well, with superposition of characteristic modes, it would be very wise to check of how the summation converges. And this is shown here. And so let's check whether our solution converges well. So first of all, as a reference, calculate the original problem. I mean, well, let's incorporate some particle feeding and calculate a current which is produced by method of moment solution. So just inversion of impedance matrix times our excitation. And evaluate a residual current, which is a residuum, which is a difference between a method of moment current and our current I, we will get if we sum up together all the characteristic modes like this. Or here you have a matrix formulation for that summation. And let's consider two summation formulas. One is the original one I was showing on the previous slide. And also, just for fun, consider weighting coefficients found with numerical projection in a least square sense as this. So you may imagine that these weighting coefficients are not the most precise ones because there are some numerical errors and so on. So if we know what is the reference solution, we can ex post find the best, the most suitable weighting coefficients for our problem. And then let's take a look at the results. Here we have a thin wire dipole of electrical size 3 pi over 4, just to change the electrical size a bit. And the excitation is placed here, so somewhere in the upper half of the dipole. And so here on the x-axis, this is the dipole itself. The excitation is placed here. And we have three different curves. We have method of moment solution, which is this curve, the blue one. You can see the nice dip here, which is caused by the localized feeder, which is placed there. And we have also a solution found with the summation of characteristic modes, which is the red line, the Harrington's formula. And also we have the blue line for the projection formula I was showing to you. And on the right, we have the residual current. So the difference between the method of moment solution, the reference one, and between our projection and Harrington's formula. And now I can run the animation here, and we can watch the convergence. Here you can see the number of modes utilized for the summation. And if I stop it somewhere, for example, let's use 50 modes, which is a lot for our problem, by the way. Then you realize that for the majority of the dipole, the summation is closely following the correct solution produced by method of moment. But here, close to the delta gap feeding, it's not the case. And actually there you can realize that there is a huge error. And this is confirmed here. If we take a look at the residual current, so the difference between the reference solution and our summation formulas, you can see that in the vicinity of the feeder, truly there is a huge numerical error, even though that we used 50 modes. And actually, there is not much what you can do with this. Because repeat once again that we used already 50 modes, and 50 modes that sit somewhere here, let's say. So here is the n number of modes used. And if we plot the eigenvalue, it's something like this. So even here for 50 modes, we are very close to something which, at least in Matlab, is very close to inf. I mean to infinity. And if you would decide to use more modes, say 100, in this case, what you get for these modes sitting here close to the modal order 100 is that the eigennumber will be numerically returned to infinity. And then if you have eigennumber being infinity, you cannot use this summation formula. So actually with the convergence, you are stopped anyway, because you cannot use more modes because of the size or the value of the eigennumber. And also you cannot use less because of poor convergence. And now you may ask, why is it so? Why this is so poorly converging? This is because we are evaluating the input impedance, which is a quantity tightly related to near field of this area. And we mentioned at the beginning that characteristic modes are very nice, very compact, very well converging series of modes for all quantities sitting outside of the smallest circumscribing sphere. So we should not wonder that this is really so poor convergence for the input impedance. Okay, maybe to support this observation and also to show you how we can easily use a summation formula for other antenna metrics, let's consider a Q factor. A Q factor is a very useful indicator of a potential bandwidth of your antenna, because it's known to be inversely proportional to fractional bandwidth. And considering no matching, this formula can be utilized. So we just perform a partial derivative of the reactance matrix with frequency, and this ratio of two quadratic forms gives you a Q factor. And Harrington actually published that we can get this information directly from the behavior of the eigennumber, because he wrote in this paper that this relation is approximately equal to the Q factor. Here, and with all the details in this paper, we are showing that it's not only approximation, but it's exactly valid if you sit at the self-resonance of your mode. Because actually, this is what you have to perform, this derivative, which is equal to this formula. And now, if you consider that lambda n is equal to 0, so you are exactly at self-resonance of nth mode, it's only this formula. And once again, you can easily compare it with the definition here, which is the definition for Q. So modal Q factor, close to the self-resonance, is really closely related Q factor of your antenna. And this can be actually very useful in antenna design, because here we have two shapes, a dipole again, a very canonical structure, and also a bow tie. And for both of them, we evaluated characteristic modes. Here are the characteristic numbers, lambda 1, 2, 3. For bow tie, we have more of them. We have 4. And you can see where, once again, you can see where they resonate. So where they cross 0 of eigennumber, how the current looks like close to these points, and the same for bow tie. And now we can evaluate, knowing how to evaluate Q, we can do it. And here you can see an ensemble of lines, here blue lines and here red lines, which are representing the modal Q factor for the first mode, second mode, third mode, and the same for bow tie. And on the top of that, you can also see a black line, which is Q factor of the method of moment solution if the structure was excited in both cases in the middle. So black line is method of moment solution of Q if the structure is fed in the middle and the bow tie is fed in the middle as well. And here you can see how to synthesize either shapes or optimal placements of your feeders. Because imagine for the first, imagine that for a dipole, feeder is placed here. Then probably it makes sense that with that feeder, we can very well excite the first mode. We cannot excite the second mode because excitation sitting here cannot excite this mode, but we can excite the third mode. And at a frequencies where these two modes are modally significant, we can probably with these modes realize Q, which will be very close to overall Q. And look. First mode is resonating here, so it's extremely significant there, and it's perfectly compatible with the feeding in the middle. And you can see that the black line is closely following to a line of the Q factor of the first mode. And then at a region where the first mode loses its significance, the black line basically stops to follow the Q factor of the first mode and jumps over to the third mode and then closely follows the modal Q factor of the third mode, because the third mode is modally significant in that area and also is well compatible with the feeding there. And then no wonder that in the second case for the bow tie, the black curve, the total Q is closely following a Q of the first mode in extremely wide bandwidth. And this is why this is so, because the first mode is perfectly compatible with the feeding place in the middle, while the higher order modes, they have, they have current there or there, but in all cases, they have almost zero current in the middle. So these three these three characteristic modes, they cannot be effectively excited with our feeder, which is placed in the middle, and therefore these three modal Q factors are not relevant for our problem. And studies like this can be easily done, and the modal Q factors can be summed up together, or with this procedure, you can extremely easily, for example, find the optimal placement for your feeders to get an antenna which has as low Q as possible. Okay, this can be done not only with Q, but it could be done with arbitrary antenna metric. And then you can really use this general formula, where once again, you can easily isolate what is the part belonging to the excitation, what is the part belonging to the modal significance of your mode at a given frequency, and what is giving you the metric itself, modal Q factor, modal radiated power, modal antenna gain, and so on. And formulating it like this, you can really easily optimize through the V vectors, for example, which are accommodating the positions of your exciters. And here, this is done on this figure for P RAT, which is the radiated power, and for W sto, which is the stored power. By the way, these two products together gives a Q factor. That's why I use them here. So omega stored energy over P RAT is the Q factor. So I only utilized these individual products from the previous study to show you once again that the radiated power is converging super fast with number of modes. You have to use just 3 modes and it's perfect convergence. I mean the convergence is met perfectly. While for the stored energy, which is near field metric, you can see that there is basically no convergence met in the first 50 modes. And you cannot met it even for 100 or 200 modes, because then you are stopped by the numerical dynamics of your problem. So once again, characteristic modes are extremely useful, but we should be very careful with near field metric, with Q metrics, because then we don't have any convergence of our problem then. This is to show you that this theory is extremely popular, vivid, and successful with truly designing electromagnetic devices we use every day. And even though I have to admit that the choice here is purely subjective, I at least try to choose applications showing the diversity and showing that the theory can be used for a plethora of different purposes. So you can see ultra-wideband antennas, mobile chassis, you can see pixelized antenna, multiport antennas, and so on. You can see pixel antennas, once again, metasurfaces, lenses, massive MIMO antennas. And all these designs were designed with the help of the characteristic mode theory. So this is really proving that this theory is very powerful and could be used nowadays. It could be used every day. Okay, so in the next part of the talk, I would focus on some advanced topics. So first of all, port mode representation, or sometimes also called network representation, is a technique which can be advantageously utilized for electrically large structures or for structures where you desperately need some compact representation of your matrix. So here, to show everything on a particular example, imagine that this is my complicated shape of a lot of unknowns. Okay, here it's just a loop, but let's consider that this loop is made of extremely many discretization elements, and then the impedance matrix is huge. So it makes no sense to decompose it into characteristic modes, because it will take a lot of time. But if I know from the beginning where my final excitation feeders can be placed, like here, I know this from the beginning, I can compress the problem a lot. And how I do it? I just say that my current density I will deal with is a product of a current density, which is an impulse response to unitary feeding sitting here, times some excitation coefficient, which I'm not sure about now, plus a current which is excited with a unitary excitation placed there, times some excitation coefficient once again. So this is algebraically shown here. And if I will move further, I realize that I can basically reduce the original impedance matrix, which is huge, to an admittance matrix, which is in this case of size 2 by 2. And such a matrix can be decomposed into characteristic modes again. So here I'm decomposing a matrix being of size 2 by 2. And still I have orthogonal far fields. My eigen numbers are showing the capacitive inductive behavior and so on. So these modes, called characteristic port or characteristic network modes, they are extremely useful. And just to support this claim, here you can see something which can be a pixel antenna if I design it properly. And I have two choices. on left, I can basically evaluate this as it is here. And then I have 730 degrees of freedom. And my matrix is of size 730 times 730, which I have to decompose into characteristic modes. Or, on the contrary, I will live with the fact from the beginning that the feeders are placed like this, which is very meaningful for pixel antenna. In that case, I have only 31 degrees of freedom, and all the matrices can be compressed to that size. And if I will decompose these matrices into characteristic mode, and if I will visualize the current densities, like here, I realize quite shocking fact that, for example, the eigennumber of the first mode is quite comparable. They are almost the same. And by the way, current densities, visually, they are practically the same. But here I decompose the matrix, which is 20 times smaller, and consider that there is a cubic algorithmic dependence on how fast is the decomposition. And for the second mode, the same valid, and for the third as well. Just compare these two eigennumbers. You have still the orthogonal far fields, and on the top of that, while here you got a vector of current densities, of characteristic current densities, and you have no idea of how to excite this current, well, where to place your feeders to excite this current effectively. I have no idea. Here on the right, you know exactly what to do. Because in your vector, which is of size 31 times 1, what is sitting inside are the excitation voltages for all these feeders. So not currents, but voltages for all these local exciters. So with port characteristic modes, you get significantly reduced algebraic problem. You have still orthogonal far fields and all the good properties of characteristic modes, and you have prescription of how to realize and how to excite this port characteristic mode directly. So a lot of advantages to think about this possibility. And of course, we have also other alternatives. For example, characteristic basis functions. They are extremely useful for scattering problems because they are basically doing the same as the network characteristic modes, but not for localized feeders. I mean that I have, for example, a loop, and I am reducing the algebraic problem not only for feeder here and feeder here into matrix of 2 by 2, but I do it for incident plane wave for this one and for this one, and I use many of them. And basically then I employ the same reducing scheme and get new matrices. So this is one possibility. Another possibility of how to reduce the size of the problem is to utilize substructure modes. And this can be used in cases when you know from the beginning that a large portion of your structure, here highlighted by the red color, is let's call it a passive structure, meaning that in the future you will not excite it with feeders placed there. And only the green part will be excited with feeders inside. And then you can employ a sure complement and reduce your original impedance matrix into matrix Z, which is of rank equivalent or equivalent only to number of degrees of freedom within the green region. So once again, you can compress the problem a lot. This is useful for problems where you have some parasitic ground plane and so on. Well, then a large class of possible extensions in recent years is reciting in area of how to reformulate characteristic modes for volumetric problems, for dielectric magnetic, and how to employ various method of moment formulations, either surface equivalences, combined field integral equations, and so on. Notice here, however, that with majority of these formulations, you may lose some good properties of original characteristic modes. For example, eigennumbers are not real valued, or eigenvectors are not real valued. Or you may be you can enter into problems where your eigencurrents are not orthogonal in far field at all. And therefore, I would be extremely careful with all these formulations. And even though they are extremely useful, some of them could have quite notable problems. Of course, this is not the case of the volumetric method of moment, where basically everything is straightforward. And here is an example of a dielectric cylinder, or to be more precise, a cut through a dielectric cylinder calculated in atom. And here are the first two characteristic modes. But unfortunately, the scaling for number of unknowns goes with Ka to the 3, which is terrible scaling for realistic applications. Typically, then you have hundreds of thousands of unknowns, and to decompose these matrices is incredible. Then much better way is probably to employ multi-level fast multiple algorithm, which has other limitations, however, as well. But this slide and all these attempts is introducing important question: whether is it possible to somehow connect finally the word of Harrington's formula and word of Garbacz formulation of characteristic modes, where one is over Z matrix and is very easy to be evaluated for complex arbitrary shapes. It's implemented in all the commercial softwares, but there are problems with spurious modes, internal resonances, and so on. And the Garbacz formula, which is unique, because there is a unique definition of T matrix. It has clear interpretation, but unfortunately is problematic to be evaluated for arbitrarily shaped obstacles. And the answer is yes, this could be done. And the link of how to put these two formulations together is a matrix we call here S1 matrix. And it's actually a matrix which is factorizing radiation matrix R appropriately. And if you are able to find matrix S1 effectively, then the T matrix, transition matrix, can be evaluated from the Z matrix directly with this formula. And to get S matrix is extremely simple. Here is the formula. It's just a simple single integration over your local basis functions and over the regular spherical waves. So it's some sort of projection from one basis to another. And then if you can evaluate this in your software, you have a framework which is, I think, something you should consider to use. So first step is to get that matrix and S1 matrix for your method of moment. Then you can calculate T matrix out of it. Then you can decompose characteristic modes directly in T matrix. So F vectors, characteristic vectors here, are directly far fields. And then, if you like, you can freely calculate characteristic currents back from your F vectors without any problem. And now you can ask why I should do that. Because you get only a very long list of advantages, which are tightly connected to a decomposition here. So, first of all, basically, you see only external resonances, because all the internal resonances with lambda eigenvalues plus and minus infinity, they have here eigenvalue equal to 0. You have extremely huge numerical dynamics, partly also because of this reason, because take a look at this figure. The commercial software, commercial solver, is the blue, is represented here by the blue markers. And you can see that the saturation of the numerical dynamics is only for the fifth digit. The academic solver, very well implemented. extremely high numerical quadrature rule is utilized, and so on. Well, more or less the same numerical saturation, because the last correctly calculated modes are roughly here. So 6 digits probably, no more. Well, decomposition of T done here, those are the red square markers, and you can see that there is no saturation at all. So you can calculate incredibly many characteristic modes precisely. Also, together with this decomposition, you get straightforward interpretation, because everything is interpreted in a basis of outgoing spherical waves. So you can deal with that directly, you can calculate far fields, and so on. Also, there are no spurious modes. They cannot exist there, because transition matrix doesn't see internal resonances and modes somehow associated with spurious modes. This is not possible. Also, it's extremely compact representation, because T matrix has a dimension, has a rank of a number of regular waves utilized for this integration. So imagine that you have extremely complicated shape, a helicopter, for example, and you discretize it into 20,000 triangles. So you have roughly 25,000 unknowns, for example. But if your Ka or electrical size is small, you may decide that you will use only 300 spherical waves to represent this helicopter in T matrix. And then Z matrix is 20,000 times 20,000 or 25,000 times 25,000. But T matrix is only hundreds times hundreds. And that's what you will decompose here. So you save a lot of computational time. And finally, it is valid for all material formulation, at least for all lossless material formulations, because it may be shown that characteristic modes for lossy materials are simply not possible, because you cannot at the same time diagonalize impedance matrix, I mean R and X, and also preserve orthogonality of far fields. This is simply not possible. Okay, and with this, we can move further, and we can also show that actually all the various representations, either the network characteristic modes, or the characteristic basis functions, or the representation of the in the T matrix, they all are basically characteristic modes. But they are only represented in different bases. Here, it's in basis of localized feeders I preset to my structure. With characteristic basis functions, I can also decompose this into characteristic modes. And then it's only represented in a basis of plane waves. And finally, characteristic modes in a T matrix are standard characteristic modes only represented in a basis of regular spherical waves. So these are three different points of view on the same problem represented in different bases. And always we can pick a basis which is the best for our application. So just to conclude here with some proper context, characteristic modes are the essential building blocks which are extremely useful for scattering problems and sometimes for antenna problems as well. They provide us with deep information about physical behavior of the scatterer. You can easily isolate building blocks, I mean current densities, you would like to utilize and those you would like to eliminate somehow by perturbing the shape or something like that. It's a very useful entire domain basis for many problems involving optimization problems, synthesis problems, and so on. And it would be good to keep in mind that there are many other decompositions which can be also utilized. I will show you some of them in a minute. And that the original definition made by Garbacz and the definition rigorously introduced is the one for the T matrix or for the scattering matrix, where you have all the good properties, let's say, and no problems with convergence and ambiguities like that. Okay, so now in the last part of my talk, first of all, I would like to mention some common misunderstandings which are related to this theory. So first, often I can read that radiation pattern orthogonality is something special to characteristic modes. And I would like to point out here that this is not the case, that actually you can have orthogonal far fields for arbitrary generalized eigenvalue decomposition, for any generalized eigenvalue decomposition, where where R is sitting on the right-hand side, and then A could be whatever. So A could be not only X matrix, it could be stored energy matrix, it could be a ohmic loss matrix, and still you will get a set of modes which are orthogonal in far field. So this is very useful property in characteristic modes, but it's not unique property to characteristic modes. Also, sometimes you can see somewhere that characteristic modes are basically modes which are fulfilling this general equation. And this is not the case. Notice that characteristic modes, this is very particular basis of extremely useful but particular properties. But we can get in electromagnetism a plethora, plenty of different modes, and there is no reason to call all of them characteristic modes. So if you are not able to prove that your algebraic properties, far field orthogonality, eigenvalues are the same as for Garbacz, and so on, if you cannot prove that, it's better to call your modes with some different name. Next, characteristic modes are not orthogonalizing stored energy. This is not possible because stored energy, as I was showing, is defined through a matrix W, as is it called here, and it's a partial derivative of X matrix over omega, normalized by omega. And then imagine the opposite, that characteristic modes would diagonalize this matrix. That would mean that you can diagonalize 3 different matrices at once. But this is extremely rare, and it's not possible if you have matrices which are not commuting to each other. And unfortunately, these matrices are not commuting. Therefore, you cannot diagonalize them together. So characteristic modes do not diagonalize stored energy. There are some other misconceptions as well. For example, that characteristic modes minimize something. And this is really not the case, because actually the Rayleigh quotient lambda, which is equal to this ratio, could be, if you start to think about it, could be set to whatever. Give me number of this you would like to have, some A, and I can do it always by combining proper modes. So if you say that this quotient should be 0, so you would like to be there, okay, I can do it by proper combination of just 2 modes, 1 mode from this region and 1 mode from this region. If you would like to have A equal to minus infinity, okay, I have infinitely many modes which are sitting at this accumulation point, and I can pick any of these modes, and definitely it will give me A equal to being minus infinity. So characteristic modes are not minimizing anything. And then we have a large bunch of potential applications and misconception with time domain. And even though I can imagine that there is something like time domain characteristic mode, so some impulse responses of your obstacle in time domain, I can hardly imagine that these modes will diagonalize impedance matrix somehow. And therefore, we should be extremely careful with calling them characteristic modes. They could be, for example, natural modes for our structure. But that's it. And let me also add that we don't have only a R and X matrix. In fact, we can introduce a lot of different matrices. We have an entire list for that. And these matrices, if they are defined via some quadratic form, they give you a metric of electric energy, magnetic energy, near field, and so on. And all these matrices are candidates for being decomposed into modes. That means that we have a lot of different modal decompositions, not only characteristic modes. We have stored energy mode. We have loop star type decomposition, where you can easily isolate loops and dipole type currents separately. We have radiation modes, and those are, by the way, shown here. We have total efficiency modes. So these modes even consider a particle placement of your excitation and matching. And still, you can decompose them into modes and use these modes, for example, for some optimization problems. We have natural modes, and we have a lot of other modes. So maybe it's a time to not consider only characteristic modes, but also start to look at different modal decompositions as well, because these may be extremely useful many times, and it is good to know about them. Okay, the very last part of this talk is actually to show you a few topics, a few challenges maybe I consider important for the upcoming months and years. The first one is related to something I call multiple orthogonalities. Because, as we already mentioned, characteristic modes are orthogonalizing R and X matrices, the real and imaginary part of impedance matrix. But maybe we would like to have more. I mean to orthogonalize not only 2, but 3 or 4 matrices together. And I mentioned that this is normally not possible because these matrices are not commuting to each other and so on. But in principle, this can be done somehow, and you can really enforce this, this property that 3 matrices are diagonalized at once, but they are not truly diagonalized in mathematical sense. You can only get orthogonal relation over some currents. However, you quickly realize that these currents do not form the entire basis. They are limited in number, and there are other limitations as well. However, still, this is a good topic for further investigation of how far we can go with enforcing diagonalization properties and orthogonal properties and so on. The next topic, which is actually happening right now, is merging modes with bounds. And well, modes, I was showing you a lot of different current density modes, characteristic modes, other modal decompositions as well. And bounds, that's a completely different topic, now very popular in electromagnetism. And research there is extremely active. And with bounds, we are typically investigating what is the best principal performance of some shape. And typically what we get is some optimal current, which is representing this, this performance. However, if you take a look at quadratically constrained quadratic program we commonly utilize for finding these fundamental performances, it's very close to modal decomposition. And in fact, for evaluating fundamental bounds, we normally use modes quite heavily. And therefore, the modal decomposition and their investigation and investigation of fundamental bounds, these two topics are now merging together, and they are creating, I would say, a bigger area of research where these two topics live together. The next topic is direct shape modification, which is, I think, the true goal of characteristic mode analysis. That normally you would take a look at a shape, the original one, which is here the rectangular plate, and decompose it into characteristic mode. And ideally, from this decomposition, you would like to collect an information of what happens if you cut a slot somewhere. So imagine that slot is cut in the middle here. And this has definitely an impact on your characteristic modes of your original rectangular plate. In this case, the first mode is almost no changed. but the second mode is changed dramatically in its eigenvalue. So on left, we have the rectangular plate. On right, we have the plate with a slot. So the first eigen number is not changed, the second is changed. And here, actually, to realize this, you would evaluate the decomposition for the shape here and for the shape here. But what I'm showing on this slide is that what happens if you cut the slot in the middle and how the eigennumber is changed can be somehow realized from the evaluation of this shape already. If you modify the eigenvalue problem slightly so that on the left-hand side, you also incorporate the ohmic-lossy matrix. And why this is done here? Because I'm saying that the future slot cut in the middle is filled with some material having ohmic losses, and these ohmic losses are parameterized by RS. And then I can differentiate with this eigenvalue problem with RS. I get this coefficient, and from this coefficient, I can realize of how this shape is sensitive to a slot being smoothly cutted there. And together with that, I can also realize of how sensitive are my characteristic modes to a slot being cut in the middle of the shape. And this is actually what we need for the geometry synthesis, because we would like to know of how characteristic modes are changed if I cut it here or there. And this information can be clearly corrected even from the original structure. Finally, the last goal, and I would call it the holy grail of the antenna synthesis, is to put everything together. So you have shape you would like to optimize. You have a feeding which you would like to synthesize. I mean to find proper places for your feeders, but also to find optimal amplitudes and phases. And you have your antenna metric you would like to boost, so to either minimize or maximize it as much as possible. And on the top of that, you have also some matching which is connected to your feeding network. And this matching is making the problem nonlinear. And to consider all these parameters together, so optimize the shape, optimize the matching circuits, optimize the placement of the feeders, that's the problem we have to address in the future. And I am sure that characteristic modes will play an important role in this resolution. And my belief is that also other modal decompositions, as well as evaluation of fundamental bounds and so on, all these ingredients have to be used together to address this problem properly. Okay, so really to conclude my talk, let me repeat that if you like, you can download our toolbox from the web page, and you can replicate all results you have seen. And there is 2D and 3D, I mean volumetric method of moment inside, and a lot of features you can learn on the web page. Notice that with characteristic modes, we have a special interested group, which is putting together almost 100 groups worldwide. We are organizing convened sessions and meetings, and this effort is coordinated by Professor Lau from Lund University. So if you like to join, please contact him. You will find the contact on the web page. Also, characteristic modes are already on Wikipedia, so you can read the article written there. And finally, in 1 month or so, we will organize European School of Antennas on characteristic modes. So if you are interested in this theory, you can consider to subscribe to this course. And please consult all the actual information on this web page. And with this, let me thank to all my colleagues I am cooperating with in the last years. And let me conclude my talk. Just remind you that all the presentations can be found on this webpage, including this PDF, so you can easily download all these slides there. So thank you for watching, and goodbye.